Okay, well, very clearly your R vector is just x minus x star I plus yj. Everybody got that instantly, which means you made great progress, even though it took a little while. Okay? What's your delta Q?
Is that going to be, so since lambda is our new charge per unit length, is that going to mean our Q over N minus our lambda? Or did I mess that up? No.
What, you said something minus something. There's no minus involved. There's no distance involved. Well, yeah, there is a distance involved.
All right, well, I messed it up then.
Is it going to be lambda over x? Of course,
Lambda over x?
No,
It would be constant if it was lambda over x. Okay, because we did state lambda's uniform, right?
Yeah.
So, just to put it on the board here, it stated the problem, but constant lambda. What do we mean by charge per unit length, and how would we use this to get the charge? What do you need in addition to charge per unit length in order to get the charge? What? I think you said it.
A delta x.
You need a length.
Yeah.
I mean, let's go back to the original words. And what length do you have? Well, you said it, delta x.
Right.
So what's delta q? Yeah. You multiply the charge per unit length times the length. That's what charge per unit length means. And in the problem that we didn't have time to do today and won't have time to do because we're already over time, there's one that involves, another one that involves a charge per unit length and a lot of symmetry, and a charge per unit area on it, still another one, okay? Now when you have a charge per unit area, then you will know that to get the charge you need
X. Like 8.
I want a word, not a symbol. A charge per unit area. So if I want the charge, I need area. Good.
Yeah.
Okay? So we have to have that. We have, that it's so simple that it escapes us. Okay? Okay, so anyhow, delta E equals what?
That's going to be our force per charge.
Yeah, well, we know that's going to be
So it's going to be
a K delta Q. We don't need a little test charge Q here because we're just going to divide it out, aren't we?
right.
Okay? Times what?
R.
Something I didn't have room, I didn't leave myself room to
Yeah.
write, but okay.
Yeah.
It's going to be,
The R vector over the R magnitude to the 3 over 2.
I might be able to write it if I write small enough so nobody can read it. Well, we got a numerator, right?
Right.
In our denominator, actually it's going to be short enough that I think we can actually do it. It's going to be x minus x star squared plus y squared, all to the 3/2. So I did have room to write it with reasonable legibility. But of course, our delta Q, which isn't going to stay there, so look at it fondly before it goes away, is what?
Oh, lambda delta x.
So what's our integral going to be?
So the to x x star to infinity, or no, wait.
Is it x star to infinity?
Or I guess the x.
And actually, see, I've got kind of
What would be just
bad
the x star
notation
to
here because I got x here, but I have an x-axis, right?
Yeah.
Okay? So I better use a dummy variable here. Okay? So I want this to be x. So my dummy variable is going to be a Greek letter. It's kind of like x. I think that's psi. and it should be x minus that.
What?
In other words,
We're changing the x for xy.
Just that?
Actually, sorry, x star.
I pick up a letter that's a little bit hard to write.
But we can keep it x axis.
Got a little carried away. Okay. Very simple. I mean, to get from here to here, except you do have to be careful to use a dummy variable down here. Okay? Because you use x here and x here, you got to get 0 for the I component. Clearly, that's not right, except it points directly above and below x star. But see, x star has to keep changing. It has to go over the whole x-axis, right? So we replace it by some symbol and integrate with respect to that symbol. And what are our limits?
That symbol is the first one, because we start there.
Limits in our integral are negative infinity to infinity,
All.
because the x-axis runs from negative infinity to infinity, right?
Right.
In other words, we have one of these for every, we partition the entire x-axis into subintervals, right? And we get a summation that would, in this raw form, look something like this. Okay? Except we might have trouble figuring out a notation for I. Well, not really. But I just go from negative infinity to infinity, right? Of course, then how many times do we subdivide? Well, you can worry about that, and you did in calculus, I think. But there's our integral for the electric field, and that's an integral you can do. Trig substitution. Okay? You can start with a u substitution. Let u equal x minus xi. You'll have it here and here, right? And then you're going to have a du, which might be more amenable to you, so you don't have to keep writing a weird symbol. Okay? But you're still going to have a u over u squared plus y squared to the 3/2, right? And here you're just going to have a constant over u squared plus y squared to the 3/2, right? Actually, it's a y over u squared plus y squared. So it's of the same form, but has a different result and a different meaning, okay, in terms of the physical situation. So there it is. So in addition to everything else, work that out for next week. For Thursday.
Wednesday.
Huh?
I'll see you Thursday.
Wednesday, okay, yeah, we can do it Thursday if you want, but Nelson won't be here. Okay, it's a straightforward integral. They're doing them right now in physics, in calculus, okay?